Greetings everyone. Welcome back to Trigonometry. Time to continue our journey into graphing trigonometric functions. Today, secant and cosecant. Now the lovely thing about these two graphs is that if you already can graph sine and cosine, which I'm hoping you already watched the lecture on that and practice those skills to perfection, okay? If you can already do those two, sine and cosine, then secant and cosecant are literally just an add-on to those graphs. Okay? You can use everything you learned with sine and cosine, and it literally just transports over into secant and cosecant with one extra step. So, I'm starting out that way. The first thing you need to remember is that cosecant is the reciprocal of sine and secant is the reciprocal of cosine. And the major important points, remember, on these were the places where it went through the axis, the center line, and the places where it had the very high peaks and the very low peaks. Remember, those were all of the quarters, right? We did quarter periods at the centers, the peaks, the centers, the low peaks. Same thing here, right? Cosine starts at a peak, hits the center, does a low peak. All of that stuff is exactly the same, and you even can start off drawing one of those to begin with. Then we just add on one extra little bit of knowledge. The fact that 1 over 1 is 1 tells me that whenever sine is 1, cosecant is also 1. So in other words, the graph of cosecant is going to share this point right here. Whenever sine is 1, cosecant is also 1. So they're going to share all of the peaks, right? So whenever this thing hit a peak over here, it's going to share that one. And same thing goes for negative 1. 1 over negative 1, they'll share those peaks too. So down here as well. All of those peaks are on both graphs. Next fact. Asymptotes occur whenever you do some sort of division by 0 in the middle of a continuous function. Specifically, vertical asymptotes happen. 1 over 0 is undefined, and typically we get either the baseball kind or the volcano kind. Okay, for these graphs, we're always going to be getting that baseball kind of vertical asymptote. And that's because from the different directions, something's either positive or negative when you are crossing over quadrants. So what's going to happen is everywhere you see the sine function go through 0, this point right here, this point right here. In other words, everywhere one of these things goes through the center line. Okay, so don't forget the center line. If it gets shifted up, it's still wherever it goes through that center line. I'm getting a 1 divided by 0 situation. And those are going to be vertical asymptotes. So you literally just draw in the vertical asymptotes. And this is that one extra step that I mentioned. Drawing in the vertical asymptotes on these functions. So from here to draw the graph of the cosecant, I literally just have to realize that whenever sine gets small, cosecant gets big, and vice versa, right? Sine is trapped in between 1 and negative 1. Cosecant is the opposite. It's trapped outside of the 1, negative 1 interval. So cosecant literally is all the way above it, all the way below it, outside of that stretch of negative 1 to 1. So then my shape is going to look like this. It's going to do what I call hug the wall and kiss the peaks. So you hug these asymptotes and you draw your shape, and you get sort of this U shape like this. And then same thing, but now it's down here, right? It has to share this peak and hug these walls like this. And then it would repeat. It's a periodic function. It would go like this. And then same thing down here, it would go up like this. Notice I didn't have to know anything else other than cosecant being the reciprocal of sine causes the peaks to match and the asymptotes to happen anywhere the sine goes through the center line. So then notice this graph that I've drawn in black here is the cosecant of x, the reciprocal of the sine function. Okay? Same exact idea for secant. If I know I want to draw a secant function, I just start with a cosine instead of a sine, because secant is the reciprocal of cosine. So the same facts hold true. They're going to share the peaks, and there's going to be asymptotes anywhere it goes through the center line. Vertical asymptotes. Okay. So then my secant function is going to be hug the walls, kiss the peaks. That, right? This would be secant of x. Would be those U shapes. Now remember, the actual cosine in here and even the asymptotes themselves don't actually exist on the graph of the secant. I'm simply using the vertical asymptotes and the cosine function itself as guides to help me draw the actual secant graph. Very typically, actually, even on the tests I give my students, I'll tell them to draw a cosine and a secant on the same graph so that I can see that they understand both without having to give a bunch of problems. That doesn't mean everybody's going to do that, but it is a very efficient way of looking at these problems. To draw a secant, it's very easy to start by drawing a cosine, but notice you don't really have to. If you know that cosine hits its peaks at the beginning, middle, and end, you could simply just put those dots there. And then if you remember that cosine goes through the center line at the first and third quarter marks, then you simply just put your asymptotes there. I draw the cosine because it's helpful to get that visual whenever you're graphing the secant, but you don't actually have to if you can just remember all of the facts about the way a cosine looks. So whatever way makes you more comfortable, right? Path of least brain resistance on that one. The other thing that we need to remark on is the domain and the range of the secant and cosecant functions. And this really starts to become important because we have to start talking about a new way of symbolizing domain, or it may not be new to you so much, but definitely unique versus some of the algebra things that you've done. Let's start with the range. On both of these functions, the range is the same, and it's pretty straightforward. You can see the range on these, the y values here, is everything above 1 and everything below -1. That's all of the y values. Just nothing in between 1 and -1. All of this is off limits for cosecant and secant. So y is going to be an element of the set from -infinity to -1. Whoops, made a boo-boo. The -1 should have a bracket because it does actually hit it. Union with 1 to infinity. So that's the range on my functions here. Both of them same range. Now the domain on each one is slightly different. If you're not familiar with writing up the domain on functions that have vertical asymptotes, I encourage you real quick to just take a brief, short look at my video in college algebra on rational functions. We write down the domain on these things, and it just shows how we can talk about how asymptotes are just cutouts of the domain. Remember, these vertical asymptotes symbolize a value that you simply cannot have. It causes a division by 0. So this value I cannot have, this value I cannot have. That would be 0, pi, 2 pi, probably, so on and so on. Not probably, it is 3 pi, 4 pi, 5 pi for this one. Whereas on secant, you can see I can't have negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2 would be the next one over there. All right. So the difference with this one versus some of those functions in algebra is that this is actually a repetitive function with a periodic function that has an infinite number of these vertical asymptotes. So you can't just write down all of the intervals. The easiest way to symbolize both of these domains is going to be talking about the numbers that you cannot have and then just making a pattern out of that. So basically what I want to do is pick one of these asymptotes to be my first asymptote, and then everything else is going to count away from them. I can use the counting numbers of the integers even to label these as like 1, 2, 3, 4, asymptote number 0, asymptote number 1, asymptote number 2, and so on and so on. This is how I do that. So for this function right here, for cosecant, the domain, I say that x is an element of. Okay, now, well, you know what? Let's scratch that for a second. Let me just do it straight up without having to do the symbols there. Let's just say x cannot be. Let's do it that way. X cannot be. Now pick an asymptote. This will be easy. I'll pick right here 0. X cannot be 0. That's true. Right here, 0 is one of your vertical asymptotes, and this is an absolutely true statement. Make sure you start with a true statement. Now add however much it takes to get from one asymptote to the next. For cosecant and secant, that's always half of a period. So plus pi. Do you notice 0 plus pi is pi, right? And then if I add pi again, see the distance between these two asymptotes, I would also be adding pi. So 0 plus pi. That's very true. 0 is, x can't be 0, and x also cannot be 0 plus pi, because 0 plus pi is pi, and this is still a true statement. However, pi is a distance. Don't think of it as a number. And what I'm going to do is I'm going to multiply that times a variable, and I'll just use n all the time. Okay? Now this is still going to be true as long as n is just some sort of counting device. I can't let n be some sort of fraction because I don't want to go part of a jump here. I want to jump from one asymptote to the next because x can't be specifically this one. X can't be this one. X can't be this one. I can only do whole number jumps of pi. I can go 1 pi, I can go 2 pi, I can jump 5 pi. Okay? So pi times n, and then you can put these 3 symbols next to your n right here. N is an element z. And what this says is that n can be any integer. My students always say, put the NEZ on there, right? It's not actually an E, it's the element of symbol. But this statement right here makes this true. And of course you could simplify this if you wanted to. X can't be in pi, if you want to put it that way. right? X can't be n pi. In this case, it simplifies to that just because anything plus 0. Okay, we'll do the next one. You'll see they don't always simplify. But you have to keep this true, that n is an element of the integers. This double line z is the set of integers, which is all of the numbers, -3, -2, -1, 0, 1, 2, 3. It's all of the whole numbers, positive, negative, and 0. No fractional, no decimal, no irrational, nothing. Okay, just the whole numbers, positive, negative, and 0. And n can be any of those. Okay, let's test it out. What would be an asymptote over here? The first one over here would be negative pi, right? That would be -1 times pi. And that's absolutely true. X can't be -1 pi. Okay? 2 pi. That would mean n is 2. N can be 2. That's great. So this is actually the most efficient way to write the domain of the cosecant function. X can be anything, but it can't be some whole number times pi, right? Some integer times pi. Let's do the domain on secant now. The domain, remember we start with x cannot be, and just pick. It doesn't really matter which one you pick. You just need one of them to start as, this is my beginning asymptote. I'm going to pick pi over 2. And this is a true statement. X cannot be pi over 2. Correct. Now, what's the gap between two asymptotes? Remember, it's going to be half of a period. And right now, we have not changed the period. Okay? Secant and cosecant have a natural period of 2 pi. So that means I'm going to be adding pi here. So, do that. Plus pi. Absolutely true. Pi over 2 plus pi, if you just add that up, is 3 pi over 2. Lo and behold, x cannot be 3 pi over 2. That's still a true statement. But don't forget, the plus pi is actually a gap size, okay? So I could add another one if I wanted to. The next asymptote would be at another plus pi. And I could add another one after that and another one after that. So it's not just plus pi, it's plus any number of pi's. So I say pi times n. Any number of pi's you wish. And we can even go backwards, because pi over 2 minus pi, that would be a -1, right? Minus pi would give me negative pi over 2. And then, of course, this is my domain. And then I have to qualify it. N can be any integer. Okay, n can't be any number, but it can be any positive, negative, or 0 whole number. Any integer. Okay? We'll go through more of these with the other examples. We'll still do more of the patterns so that you'll see. And basically the idea of this is going to lead you into eventually when we start talking about solving trigonometric equations, and you'll see that these things are supposed to also sometimes have patterns that work just like this. So this is a very common thing, and something you definitely need to know how to write down this kind of pattern in most of your trigonometric work. Let's begin our GeoGebra trek with a view at those two basic graphs. Cosecant being the reciprocal of sine. You'll notice the GeoGebra doesn't even bother graphing the asymptotes there, but I can punch up y equals sine of x so that you can see the way that they do actually fit there. Let me go ahead and dash the sign there so that you can see truly that cosecant does actually fit into the sine curve the way that we discussed. And on top of that, there are asymptotes that the cosecant obeys that happen every whole number times pi. You see 0, pi, 2 pi, 3 pi, so on and so on. And you'll notice even the way that I told GeoGebra to do the vertical asymptotes was x equals n times pi. I couldn't do all integers because GeoGebra doesn't have that concept of infinity, but I did tell it to count -6 to 6 on the ends, and you see it did actually give me these particular asymptotes. Next, we'll take a look at secant. Again, you can see the secant is the reciprocal of the cosine. Let me go ahead and punch up cosine for you. You can see it does indeed fit into the pattern of the cosine the way we discussed. And of course there are asymptotes for the secant. They happen to be at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. And again, the way I programmed it was the 1 plus 2n times pi over 2. That does give us the pattern for all of the asymptotes that are not in the domain. Let's get 2 examples going here, and then in the next scene I'll do 2 more examples that have everything in them. These 2 examples just do some of the basic stuff, just the stretching, if you will. Right? So we'll stretch first. Pun intended. Okay, so anyway, -3 cosecant 4 pi x. If you've been asked to graph a cosecant function, in your mind, the first thing that you want to think of is, okay, well, cosecant is the reciprocal of sine. So what I'm going to do is graph -3 sine 4 pi x. This is what I'm actually going to graph. And then remember, it's just that one extra step past the sine function where I'll draw on the asymptotes, hug the walls, and kiss the peaks. Okay? So I'm just going to graph this first. Well, this is the skill that you already have, right? We approach, we get the period, the quarter period, we set up our x-axis, get our numbers, set up the y-axis, fill in the shape. Let's do it. The period is going to be 2 pi divided by 4 pi in this case, right? Because 4 pi is my frequency number here, which is 1/2. So then my quarter period is going to be 1/4 times 1/2, which is 1/8. So I'll be counting by little sections of 1/8. I'll set up my x-axis. My x-axis here, and remember I always start with 5 marks. 1, 2, 3, 4, and 5. Let's get a little bit nicer there. Okay, so there's 5 marks. And remember, if you need 2 periods, it's okay, just put 4 more marks, right? This will be my x-axis here. It has not been shifted left or right. And remember, sine is going to start at 0. So this is 0 is my first mark there, which means this is also where my y-axis is going to be. Helpful to know. There's my y-axis. And I'm going to be counting by eighths. So 0 plus 1/8 is 1/8, then 2/8, then 3/8, then 4/8. And 4/8 is 1/2, which we know to be a period of this particular function, right? Okay, my amplitude is 3, so let's go ahead and mark that in. I'll go 3 above and 3 below. 3, -3. And also don't forget the negative is a reflection. Okay, so now I'm ready to start drawing in my shape here for the sine. Remember, sine starts in the center, so that's the first point. Then at the first quarter, it's at a peak, but it's reflected. So instead of going up, I'm going to go down first, which means it's going to hit here. So then it's going to come back up to here. Then it's going to go up to the top. And then it's going to be back at the center again. So basically, something like that would be my sine shape. And in this case, I'm just going to leave it dashed because that's not actually my real graph, is it? That's the graph of the sine that I'm using to help myself in the shape of this thing. So then I remember, oh yeah, everywhere it hits the center line, I'm going to put a vertical asymptote. So that would be at 0, at 2/8, and at 4/8. Okay, so actually let me go ahead and extend these asymptotes a little bit further here to help me draw these a little bit better. Alrighty. So then now I'm switching back to the actual cosecant, which means I need to hug the walls and kiss the peaks. Whoops, should never cross that asymptote like that. That. Okay, and then same thing down here. Like so. Okay, and again, if you need more periods, more cycles, just put more marks. You'll draw more asymptotes, hug more walls, kiss more peaks. And you know, it's just going to keep repeating that shape over and over again. It's a periodic function. So the only other thing to discuss would be the domain and the range. Okay, well, the range, as you can see, is going to be above 3 and below -3. So let's write that in. My range is where y is -infinity to -3, union 3 to infinity. So here's my range. The domain, if you recall, we have to do the pattern where we say what x cannot be. X cannot be, well, it looks like 0, and then 2/8, which is 1/4, and then 4/8, which is 1/2. And then what do you think the next one after that would be? Well, let's think about this for a second. Start with the easy one, 0. Is this a true statement? X cannot be 0. Yes, that is true. Then, what is the distance between one asymptote to the next? From here to here, 2/8 to 4/8 is a total of plus 2/8. Okay? So I'm just counting because that's the way I have these counted out, right? If you want to reduce this to plus 1/4, that's fine. But that's going to be the constant distance between every set of asymptotes, both directions. So that means I'll have 0 plus 1/4 times n. And of course, n has to be any integer. And that's going to be my domain here. X cannot be 0 plus 1/4 times n, and n is any integer. Again, if you want to simplify that, this would just give you n over 4 plus 0, so it's just n over 4. Or you can leave it like that. Whatever way makes you feel more comfortable. All right. Secant. Again, when you approach something like this, you have to remind yourself, hey, I'm really graphing just the reciprocal of cosine. So this is what you should be thinking. I'm really graphing for cosine 3x to start with. That's what I'm graphing to start with. And then, of course, what I'm really graphing is actually the secant, but, you know, we'll just draw in the extra step. So then what's the period here? Period is going to be 2 pi divided by 3, right? The number in front of the x, I mean, not the number in front of the whole thing. So then what's my quarter period? That's going to be 1/4 times 2 pi over 3, which is going to give me pi over 6. Okay, so that's my quarter period. That's what I'm going to be counting my quarters by. Again, it's not shifted left or right, or up or down for that matter. So I'm going to be starting at 0. Okay, so here's my x-axis. And I'll put my 5 marks on there. All right, there's my 5 marks that I want to use. And I am starting at 0. So I'll go ahead and put my y-axis here. You can make it as tall as you want for comfort's sake. And my amplitude here is 4, so I'll go ahead and draw that in. So here's 4, here's 2, here's -2, here's -4. Good deal. Boy, even that was kind of tall looking, huh? Tell you what, let's scale it. Let's scale this just to make it easier on ourselves. Let's make this 2 and this 4. How about that? Yeah. So -2, -4. Okay, so I've got my y-axis scaled. Let's do our countings on the x-axis here. Remember, the gap is pi over 6. So 0 plus pi over 6 is pi over 6. Then add another one, I'll have 2 pi over 6. Add another one, I'll have 3 pi over 6. Add another one, I'll have 4 pi over 6, which you'll note, right, that is 2 pi over 3. Okay, from here, I'll want to draw the cosine in. Remember, a cosine starts at a peak, then goes through the center, then bottoms out, then through the center, then back to the top peak again. So my cosine whoops, a little bit weird right there. Okay, so there's the cosine shape that's going to help me draw this. Let's put in the asymptotes, right? The asymptotes are going to be wherever it crosses the center line. I'll go ahead and draw these a little bit lower. Okay, so then for my secant graph here, I'm just going to want to hug those walls and kiss the peaks, right? Okay, so let me see if green works here for us. Nope, that's not showing up very well. Sorry about this. I'm just going to have to switch back to, yeah, let's just use black. That's fine. Okay. And then, of course, it does actually go up to another one this way. Don't get it confused with the y-axis right here. This is the actual graph right here. That was the reason I didn't want to use the black marker there, because I didn't want to get it confused with the axis. But it looks fine. See, I'll put my little arrows here to point that out. And then, of course, it's here. You'll notice on the secant, I sort of get my upward bend here split. Of course, you have to use your imagination that it does actually continue on in that pattern there. Okay, so the only other thing, again, that we want to talk about is what's the domain and the range here. So again, the range is pretty straightforward. The range is just going to be where y is outside of the cosine region. So it's going to be negative infinity to negative 4, union 4 to infinity. And then what about the domain? Again, I just need to pick what x cannot be. So pick a starter. Pi over 6 seems like it's a good starter, right? So x can't be pi over 6, that's true. What's the distance between the two asymptotes here, right? The distance between these two asymptotes should be half of a period. Well, a period is 2 pi over 3, so half of that would be pi over 3, right? Or do it this way. Pi over 6 to 3 pi over 6 is plus 2 pi over 6, which, don't forget, that's the same thing as pi over 3. Okay? But you know what? Pi over 6 is this here. I think I'm not going to use the simplified pi over 3. I'm going to use the 2 pi over 6 plus 2 pi over 6 times n. Because remember, we can jump however many 2 pi over 6 gaps we want. And then I just need to make sure and qualify n as any integer so that all of my jumps are whole numbers. You may wonder why I chose this one right here, but I want these denominators to be the same because you can, in some schools of thought, they prefer to have this simplified. You can actually simplify the way this looks like this. I can actually factor out the pi over 6, and it would be 1 plus 2 times n, like that. It's okay to leave it like this, but you can also factor it out and make it look like that, which is why I stuck with the common denominator. Okay? So a couple of basic graphs. Go take a look at Geogebra, what they really look like, and then let's do the last two examples. Okay, so now we're taking a look at the next two graphs here. I have y equals negative 3 cosecant 4 pi x. And of course, when I activate that one, you can see it gets very, very jumbled. The period on this is 1/2. So literally, one whole cycle is going to fit into this small little stretch right here. So then what I need to do is change my numbering system. On my numbering system, I'm going to change it to what my quarter periods were, which were the 1/8. And then I'm going to stretch out the graph so that we can focus in on a smaller number of cycles on the screen at a time. Alrighty, so here we are right here. It's only a few cycles on the screen now. And I can go ahead and throw the asymptotes for it up there as well. And you'll notice that the way I programmed the asymptotes was just n divided by 4. And that's because the asymptotes started at 0 and there was a gap size of 2/8 or 1/4 between each one. And as we saw on the graph, it does start in the downward direction and then to the upward direction first. You can see that my cosecant started reflected there. It does have an amplitude of 3. You can see it peaks out at positive 3 and at negative 3 here. And that's what our graph for that looks like. Okay, next, let's turn this thing back into a standard graph here. And let's get our graphics back to the way it looked before. And then when I turn on the 4 secant 3x, you'll notice these aren't quite as badly spaced. However, I do want to be able to see the important points, the important locations here. Notice they're not on the whole line markers. So again, I'm going to lean on the fact that my period was 2 pi over 3, which then caused us to have a quarter period of pi over 6. So I'm going to start numbering these as pi over 6s so that I can take a closer look and actually get a smaller number of cycles here. Let's move this here and stretch this out. Alright, So again, by counting by pi over 6s, you can see all of the important places. And then here are my asymptotes. And I numbered it by doing the 1 plus 2n times pi over 6 there. Again, the amplitude was 4, so you can see it peaks out at the 4 and -4 marks. And it does actually start at the top like a cosine would, then goes down, then back up, then down, then back up. Let's finish up with two last examples that have a lot of, like, just all of the different things that can come at you with these types of graphs. So y equals 1/2 cosecant of the quantity 2 pi over 3x minus 4 pi over 5. So don't forget, in the parentheses, you always want to have that frequency number factored out so that your horizontal shift, your phase shift, will be correct. And I perform that factoring, remember, using division. So right here, I'm going to divide 4 pi over 5 by 2 pi over 3, which is going to be 4 pi over 5 times 3 over 2 pi, which I hope you'll notice will leave me with a 2 in this numerator and will give me 6 over 5. So when I factor here, I'm going to be left with a 6 over 5 as my shift. So y equals 1/2 cosecant of 2 pi over 3 times x minus 6/5. This is what we'll be graphing. And remember, with cosecant, I'm actually going to graph a sine first, and then I'm going to use the properties of that sine to graph the cosecant. Okay, so if we can, let's go ahead and get 2 periods out of this one for good practice. I need the period first, so my period is going to be 2 pi divided by the 2 pi over 3, right? My frequency number here. That's going to be 2 pi times 3 over 2 pi, which is going to give me 3. Alrighty. So then my quarter period is just going to be 1/4 times 3, or 3/4. Okay, so now I have the quarter period, and so I can start putting down my marks on my axis. So let's see, let's get a decently sized x-axis here. And just so that I can facilitate 2 periods, remember, I'm going to do my 5 initial marks, and I'm going to put 4 more to have that second cycle to go on. Okay, so 1 mark, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, this one has been shifted to the right by 6/5. So here's what I want to do. I want to be able to find my y-axis, and since this thing was shifted to the right, that means my axis is going to be somewhere over here. So here's what I want you to think of, that these 4 marks don't exist yet. Remember, I usually start with 5 marks, right? These are the 5 marks that I'm going to start with, and my 6/5 is going to be right here. That's where I've been shifted to. Okay? Now, of course, my quarter period is 3/4, which means to get to this next mark right here, I'll have to do 6/5 plus 3/4. Well, I don't have a common denominator yet. So what I'm going to do is I'm going to change everything to common denominators right now before I even, look at doing any of that. So to get the common denominator here for 6/5 and 3/4, I'm going to notice that 5ths and 4ths have a common denominator of 20ths. So I'm going to change this into 20ths by multiplying by 4. That's going to give me 24 over 20. That's the same as 6/5. And 3/4, I'll do times 5 for each one. That will give me 15/20. Right? Okay. So now I'm going to do my counting using the 20ths. Okay? And I'm counting by 15s here. So 24 plus 15 is going to give me 39/20. 39 plus 15 is going to give me 54/20. 54 plus 15 is going to give me 69/20. And then 15 plus 69 is 84/20. Okay, so 6/5 plus 3 is a full cycle, right? And 3 is 15/50. So this should be, I'm sorry, not 15/5. 15 and 6 is 21. So this should be 21/5. And you'll notice that it is. If I divide by 4, this is 21/5. All I'm doing is I'm demonstrating that we did actually go a distance of 3 here to 21/5. So these are my actual official marks, right? And so now what I'm going to do is I'm going to count backwards as well, using the 15/20 for each mark. So 24 minus 15 is 9/20. Then 9 minus 15 is going to be negative 6/20. Minus 15 is going to be negative 21/20. Minus 15 again is going to give me negative 36/20. Okay, so now I hope you'll see why I did, the 5 marks. Here are my beginning 5 marks, and I went backwards for my second cycle so that I could run into the negative numbers and I can actually put my y-axis here. All right, so then my y-axis is going to be somewhere like this. Okay, so the 6/5 here and the 21/5, that's nice little, I'm going to get the 21/5 out of the way. Just remember the 6/5 right here, this was my starting point. Okay, that's why I'm going to leave that one marked. My amplitude is 1/2. So in other words, if I were to put 1, right, 1/2 would be here. So if I do that same thing, negative 1 is here, then negative 1/2 is right here. And that's actually the amplitude of the sine and the cosecant. You could kind of call it amplitude. Okay? So let's draw in the starting point. Cosecant, the reciprocal, is sine. So that means it starts in the center. Here's the center, right here. And then sine starts by going up to a peak. The peak is right here at the 1/2 mark. Then back to center. Then down to the bottom peak, which is at negative 1/2 right here. And then back up to center. So the sine should look like this. And then, of course, it's going to do the same thing going backwards. It will be down, then back up, then up, back down like this. So there's 2 cycles of the sine portion. Okay, but we're not interested in the sine. Remember, we want the cosecant. So let's see. I need asymptotes. That's going to be anywhere it crosses that center line. So 6/5 is a vertical asymptote. 54/20 is a vertical asymptote. 84/20 is a vertical asymptote. Negative 6/20 is a vertical asymptote, and negative 36/20. Also a vertical asymptote. Okay, so now I want to draw in my cosecant graph. Let's see if purple shows up really well. So now I hug the walls and kiss the peaks. Okay, so that's going to be up here. Down here. Can't see this one as good, as well as the other one, right? But there's my graph on that one. Let's see, up here. And down here. Like so. All right. So there's the actual graph, the thing that I've drawn in purple here. All right, so the only thing left, as we have been doing before, is to talk about the domain and range of this graph, just so we can get the practice in on that, right? The range of this graph, y is an element of anything from negative infinity up to negative 1/2, union 1/2 to infinity. Right, that's this piece up here. And then my domain. X cannot be. Well, why not start with our shifting point right here, right? 6/5. X cannot be 6/5. Now, what size gap is it from one asymptote to the next right here? It goes from 24/20 to 54/20 for a distance of 30/20. 30/20. This has a denominator of 5 on it. Can we reduce it to that? Let's see. Probably not. I'd have to divide by 4. That's not going to work out. So let's do this. Instead of this, you know what? I'm not going to bother with changing anything. Let me go ahead and reduce this. 30/20 is 3/2. That's the size of the gap between the two. So 6/5 plus 3/2 times n, and n can be any integer. So there's my domain. Any number that falls into the set where 6/5 is going to be added to any integer times 3/2. Right? 6/5 plus 3/2 is going to be the 54/20. 6/5 plus 2 times 3/2 will give you the 84/20. 6/5 times negative 1 times 3/2 will give you the negative 6/20. Okay, so they're all accounted for this way. You can simplify that if you really, really want to, but that's a perfectly acceptable version. Okay, let's separate this here. And then let's get started on the next function here. H of t is, whoops, made a boo-boo. I hope you caught it. Should be a t, not an x. H of t is 1 minus 2 secant of 5t plus 3 pi. All right, so just like before, remember we want to adjust the frequency number so that I can get the correct horizontal shift here. H of t is equal to 1 minus 2 secant of 5 times t plus 3 pi over 5. I just divided by 5, and in this case, nothing was simplifiable, so I just left it as 3 pi divided by 5, or 3 pi over 5. So then my shift is actually 3 pi over 5 to the left. Next, we need to look at what the period is, and I need to also know what to expect. Don't forget this 1 is added in the front. This is a shift upward. Do not do 1 minus 2. The 2 is attached to the secant. The 2 is my amplitude, and the negative is a vertical reflection. Okay, so let's do the period now. The period of this is going to be 2 pi divided by 5. The frequency number, right? Nothing to simplify there. That's the period. So what's the quarter period? Quarter period is going to be 1/4 times 2 pi over 5, which is going to give me pi over 10. So there's my quarter period there. Okay. Just like before, do you notice that the quarter period does not have the same denominator as the shift? So I'm going to have to do a little bit of denominator work there with my numbers. And let's try to get 2 cycles of this one just like we did in the last one. Okay, so x-axis, and I'm going to put 9 marks on there. 2, 3, 4, 5, 6, 7, 8, and 9. Okie dokie. I know they're not perfectly evenly spaced. I'm doing the best I can here. I was shifted negative 3 pi over 5. That's a shift to the left. So that's what I'm going to put here, negative 3 pi over 5. I'm going to start over here. Since it's on the negative side, I'm going to be counting towards the positive numbers. Hopefully I find a spot where it switches to positive, and I'll be able to put my y-axis. If not, then I can always do like I did in the last video. I hope you noticed you can actually separate, do a little ellipse symbol, and just put the y scale over there if we need to. All right, so then next I'm going to be saying that I will get to this gap number right here by doing the negative 3 pi over 5 plus pi over 10. Okay, so the first thing I hope you notice is that they don't have the common denominator like we said before, which means I'll need to convert this one into tenths. So let's do that. Negative 3 pi over 5 is the same thing as negative 6 pi over 10. And then I'm just going to be adding pi over 10 every time. Well, that seems pretty straightforward. I'm just going to be adding pi over 10 now. So negative 6 pi over 10, I'll go to negative 5 pi over 10, then negative 4 pi over 10, negative 3 pi over 10, negative 2 pi over 10, negative pi over 10. Hey, that's cool. We're going to hit 0, right? Because I add pi over 10. Then I add it again, I'll get pi over 10 and 2 pi over 10. Okie dokie. So when everything is said and done, a whole period should last 2 pi over 10. So starting here, if I go 4 marks, 1, 2, 3, 4, I landed at negative 2 pi over 10, which is actually negative pi over 5. Right? Well, 2 pi over 5 plus negative 3 pi over 5 is negative pi over 5. So that is indeed one period right there. And then I have 4 more marks where I land at positive pi over 5, which again brings me another 2 pi over 5 in that direction. So those are good numbers for this. I am actually traveling the correct amount. So now I see 0 is here. Let's go ahead and put my y-axis here. I know my line's slouching a little bit. This is all by hand, and that's why I love being able to do the Geogebra after this, because it draws it way better than I do. But this is still a good skill to have. You need to be able to find these numbers and to be able to write them out like this. Okay, my amplitude is 2. So let's go ahead and symbolize that. 1, 2. Oh, I made a boo-boo. Can't do the amplitude yet. We got to do the vertical shift of 1. All right. So actually, cool. I'm going to get this out of the way. I have a new center line, right? My new center line is positive 1. So this is my actual center line here. right? Because it's a vertical shift upward at 1. And then my amplitude is 2. So I'll need to go 2 above that and 1, 2 below that. So this is going to be -1. This is going to be +3. And of course, this is +1 right here. Okay, so now I'm ready to put in the cosine portion, right? This is a secant, so I want to draw a cosine. And remember, for cosine, I start on a peak. My shift was to the -3π/5 right here. So that's where my cosine will begin. Let's do it in red. Don't forget, this one was reflected, right? So then my cosine's actually going to start at the bottom, because cosine normally is at a peak, goes down, then back up. We're upside down. We're flipping this thing. So at -6π/10, I will be at the bottom, which is here. Then I will be in the center line, right, because it was shifted up. Then I'll be at the top, which is going to be at 3. Then I'll be back to center line, then back to the bottom again. This one needs to move up a bit. The number's in the way here. There we go. Okie dokie. Then I'll be back up to the center, then back up to the top, and then back to center. And 2π/10, I'll be at the bottom again. Okay, now remember, I need the asymptotes in order to graph the secant part. My cosine technically is just doing this. Approximately. My secant needs the asymptotes. That's going to happen every time it goes through the center line, not where it goes through the axis, where it goes through the center line. So it's still on that important number, quarter number that I've listed there already. This is going to be an asymptote at -5π/10, at -3π/10, at -π/10, and at π/10. So then, to draw in my secant graph, I'm just going to hug the walls and kiss the peaks. So that's going to be here. Right? It's going to go this way some. That's going to be here. 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 And here. And of course it's going to keep going that way forever, right? Okay. So then the only thing left to do is to just, recognize the important points. Notice I do have a low peak at -6π/10, a high peak at -4π/10, a low peak again at -2π/10, so on and so on. And then from here, I'm just going to list out the domain and the range. Domain, x cannot be, and let's pick an easy one. Let's pick π/10. That's a true statement. Plus, how far is the gap between any two asymptotes? So the gap from here to here is literally 2/10, or 2/10 pi, 2π/10. And since that has the same denominator as what I'm going with here, I'm going to leave it that way. So 2 pi over 10 times n. And I'm just going to say that n has to be any integer z. Okay, so then you can, of course, simplify this if you wish to 1 plus 2n times pi over 10. Either one of those is fine. Okay, what about the range? The range is important to note on this one too, especially because it was shifted upwards. The range here is going to be where y is an element of negative infinity up to -1 here. Union with this one, notice it starts at 3, goes up to infinity. So it's definitely important to note the range on this one because it was shifted up. The center line is at y equals -1. I'm sorry, +1, y equals +1. But then the range is outside of +3 and -1 on that one. Okay? So I hope this lecture has shown you how easy it is to get to a secant or a cosecant graph just by knowing already how to effectively graph a sine or a cosine. Stay tuned for the next lecture on tangent and cotangent graphs. Let's finish up with the GeoGebra look at these two graphs that we were just doing. First, let me just show you the cosecant shape here with the given asymptotes that we did actually calculate. I have 6/5 plus 3 over 2 times n as my generator for the asymptotes, just as we did with the domain. And as you can see, the graph does actually fit there. And you can even tell that the amplitude is 1/2. You can see right here. In fact, I'll help that out a little bit. Let's take a look at the y-axis being scaled to 1/2. So as you can see, the amplitudes do actually fit into the 1/2 and -1/2 marks here on both of those. Let me stretch it a little bit for you so that you can see it there. 1/2 and -1/2. Okay, so then to look at the rest of the special marks, like where are the peaks and the asymptotes really, we have to do 20ths. And GeoGebra can only count by the same unit everywhere. So doing this makes a really thick swash of lines to look at. So we have to really zoom in a bit to make this work, which is going to make the graph stretch outward a good bit. Alright, so that you can see the asymptotes are in the correct spot here. Right, you can see this asymptote is at 6/5, and this asymptote is at the 27/10, which is the same thing as 54/20, and so on and so on. You can see that the peaks here, let me go ahead and squish it in a bit. You can see the peak here is definitely at the same value there. I need to stretch it out a good bit though, so that you can see the 39/20 here, and the 9/20 here, and then even on to the negative side, right? Right here we had the -21/20 there. Okay. So now let's shrink this back to normal size here. Let's do standard view, and then let's get the graphics back to looking the way it did before for both of these axes. And let's turn these off. So the next graph we were looking at was this secant graph. And again, you can see it looks very jumbled in there. And I use the sequence 1 plus 2n times pi over 10 to get the asymptotes of this one. I am going to stretch it out a bit for us here so that we can see individual cycles here for this one. And then we're going to want to change our x-axis numbering so that we can get a good view on that one. We're going to do pi over 10 for that one. Okay, and then the next thing you also need to notice is that this has been shifted upwards. You can see that this one peaks out at 3, and then these bottom ones peak out at -1. The center line of that being 1 here. They are oscillating in the way we would expect. The thing starts right here with a peak on the mark there, and then at pi over 5, and then at 2 pi over 5, and at 3 pi over 5 we have the peaks in those spots there, the way that we were discussing before. Okay, and then of course the asymptotes being on pi over 10, 3 pi over 10, and that's how I was able to number them the way that we did using the tenths.